Good morning everyone. Today we are going to see neural networks based feedback linearization control algorithm. The organization of this lecture will be as follows. First, we will see the gist of feedback linearization. What is feedback linearization? We will first see. Then we will see neural network based feedback linearization, where there is a theorem to justify this control algorithm and the verification of this theorem. Then we will see the neural network based feedback linearization for f of x known, which is basically a nonlinear function associated with the controller being unknown, and g of x being known. So, we are going to take a case where the nonlinear function f of x is unknown and g of x is known, with the approximation, the error approximation term being 0 and being non-zero. Under these cases, we are going to define or derive or design the neural network based feedback linearization approach. Let us start. First of all, let us talk about feedback linearization approach. Let us consider a family of single link or single input, single output affine system expressed by the given equation x1 dot equal to x2, x2 dot equal to x3, it continues xn dot equal to f of x plus g of x into u, and y is a system response given by x1. Let this equation be number 1, which is defining a family of single input, single output affine system. Here x equal to x1, x2 up to xn, which belongs to the n dimensional Euclidean space, and y belongs to 1 dimensional Euclidean space, and u also belongs to the 1 dimensional Euclidean space. So, the objective here for this feedback linearization based controller approach is that to find a control law such that x follows the desired given trajectory, x desired. That is the objective of this controller. Now, let us define a variable, called filtered tracking error, which is represented by r, that is given by r equal to n minus 1th derivative of the tracking error e plus lambda 1 n minus 2 derivative of the tracking error continues up to lambda n minus 1 into e. Here, as I mentioned, e power n minus 1, which is nothing but the n minus 1th derivative of tracking error e, and E is nothing but the output tracking error, that is given by E equal to y desired minus y, desired output minus actual output of the system. Now, by choosing the control algorithm, choosing the control law, you can say precisely control law, which is given by u equal to 1 by g of x into minus f of x plus kvr plus lambda 1 multiplied by n minus 1th derivative of the error, and it continues plus lambda n minus 1 first derivative of E plus x n d dot, that is a derivative of the desired state, nth state. So, by choosing this control law, the closed loop error dynamics becomes r dot equal to minus kv into r, which implies that it is stable and linear. Okay. By choosing this control law, we have the closed loop error dynamics becoming linear as well as stable, that is given by this expression r dot equal to minus kv into r, where kv and the lambdas are chosen positive design parameters, so that your r dot is negative, all right. And such an approach is called feedback linearization control approach. Okay. So, this is the fundamentals of feedback linearization. Now, let us talk about the condition when f of x is unknown and g of x is known. So, there is something that with the feedback linearization algorithm approach or technique, there is a problem associated when either the nonlinear function f of x is unknown or g of x is unknown, or both g of x and f of x are unknown. So, we go for the function approximators to estimate the unknown functions f hat or g hat by neural networks approach or fuzzy systems. Okay. Again I repeat, for the feedback linearization there is a general problem which is associated when any of the nonlinear functions f of x or g of x or both are unknown. So, in that case we have to go for the function approximators such as neural networks or fuzzy systems in order to estimate the unknown function, and the estimated function is termed as f hat or g hat. Then the controller parameters can be updated in such a way that the closed loop error converges to 0. That is what it is. Again I repeat, the controller parameters can be updated in such a way that the closed loop system error becomes 0 or converges to 0. So, here in this concept, let us assume that only f of x is unknown, but g of x is known. So, the output of the neural network, if you consider a neural network in order to approximate the function which is unknown, then the output of the network is considered as the estimated value of f of x. So, the output of the network could be represented f hat of x, where x is the input. Here we approximate f of x by using a radial basis function network, which is the neural network. We consider that, okay, because it is simpler and also it is essential to estimate the unknown function for our particular motto. Okay, let us consider an n input and one output RBFN. Let us consider an n input and one output radial basis function neural network shown by this is x1 of k, xn of k hidden neurons, output neuron. The output is f hat of x of k, which is the approximation of the function f of x of k. Okay. So, by this neural network, which is an n input and one output RBFN, we are approximating the unknown function f of x. So, let us term this hidden layer by phi 1, phi 2 up to phi L. So, the weights, the network weight will be, the network weights will constitute a vector w hat that belongs to the space R of L cross 1, which means it belongs to the space of size L cross 1 in this case. Okay. So, the weight vector is associated with this, you can see. Okay. So, this is the thing that, and we all know that the output is basically the linear representation of the weights associated with the output of the hidden layers. Okay. So, now in this case we have the strong notion that f of x is unknown, but g of x is known for the system that is expressed in the very first slide, which is system number 1 given by the expression equation 1, which is the input affine system. So, let f of x be approximated as f hat of x, which is equal to w hat transpose phi of x using a radial basis function network, because the output of the radial basis function network is given by the product of phi of x, which is the output of the hidden neurons multiplied by the weights connecting the hidden layer to the output layer. Okay. So, those are the estimated weights, that is why it is w hat. Okay. So, now the control law is given by u equal to 1 by g of x multiplied by minus f hat of x plus kv into r plus lambda 1 into n minus 1th derivative of the tracking error plus lambda 2 into n minus 2 the derivative of the tracking error, and it continues lambda n minus 1 first derivative of the tracking error plus x n d dot. Will this control law will stabilize the system 1 given by equation 1 in the sense of Lyapunov stability, in the sense of Lyapunov stability analysis, provided W hat is updated using an approach called W hat dot equal to minus gamma into phi into r, where the gamma is a positive definite matrix. Okay. So, we have to have the W hat to be updated at every instant, and the W hat dot is the update law here. Okay. So, that is the situation here in order to approximate the function f of x, so that the network output is f hat of x. Okay. So, now let us see that a theorem where this control proof has been briefly proposed by this theorem, say it is theorem 1, which is stating this control logic, that is feedback linearization by an RBFN network. The theorem 1 states as, let the output tracking error E be given as E equal to y desired minus y, which is equal to x1d minus x1, where y desired equal to x1d, okay, it is x1d, which is the desired output of the system. Okay. First of all, in the theorem let us define the output tracking error E, which is nothing but the discrepancy between the desired output minus actual output of the system, where the desired output is 1 x1d and the actual output is x1, y equal to x1. Now, let us talk about the filtering error. The filtered tracking error is given by r equal to n minus 1th derivative of the tracking error plus lambda 1 into n minus 2 derivative of the tracking error, and it continues up to lambda n minus 1 into the tracking error. Say this be equation number 2. Here lambda 1, lambda 2 up to lambda n minus 1 are chosen such that equation 2 represents a stable dynamics, okay, such that equation 2 represents a stable dynamics by choosing lambda 1 to lambda n minus 1. And we know that n minus e power n minus 1 is given by the n minus 1th derivative of the tracking error E. Now, the objective here is to achieve a satisfactory tracking performance, as well as maintaining the boundedness of the weight vector of the neural network W hat and the error. So, this is the objective for this control design, which is to achieve a satisfactory tracking result, and we need to maintain the boundedness of the neural network weight vector W hat as well as the tracking error. So, now let us continue this. So, in this case the control law is defined as u equal to 1 by g of x into minus f hat of x plus kv into r plus lambda 1 multiplied by the n minus 1th derivative of the tracking error plus lambda 2 multiplied by the n minus 2 tracking error, derivative of the tracking error, plus it continues lambda n minus 1 into first derivative of the error plus x n d dot. Say this be equation number 3. Here f hat of x is given by, we know that w hat transpose multiplied by phi of x, which is nothing but the response of the neural network response or the output of the neural network. Let us assume that there exists an ideal weight vector, W such that the original function f of x can be represented as f of x equal to W transpose phi of x, where W is the ideal weight vector corresponding to the original function. Now, as per the properties, as per the approximation or the universal approximation property of neural networks, for any smooth function represented by f of dot, there exist weights such that f of x equal to W transpose phi of x plus epsilon, where epsilon is called the estimation error. Okay. So, now it is assumed that the estimation error is 0. It is assumed now, as of now, that the estimation error is 0 for our current case. We are going to consider in the end of this lecture that the estimation error is non-zero. What will happen to the control law? Now, this assumption will hold for comparatively less complex nonlinear functions. Which are less complex comparatively. Okay. So, if we take a sufficiently large number of adjustable weights, okay, if we take a large number of adjustable weights. Okay. So, this assumption where epsilon equal to estimation error is 0 holds true for nonlinear functions which are less complex and there are sufficiently large number of adjustable weights associated with the network. Okay. Now, let us continue this with the approach that now substituting the control law given by equation number 3 into the system, which is the original input affine system given by equation 1, we get x n dot equal to f of x plus g of x multiplied by, I am putting the u expression control law, 1 by g of x into minus f hat of x plus kv into r plus lambda 1 n minus 1th derivative plus lambda 2 n minus 1 second derivative of e, and it continues lambda n minus 1 first derivative of e plus x n d dot, which is given further by, we know f of x will have the ideal weight vector given by w transpose phi of x. W transpose x minus f hat of x is given by w hat transpose phi of x plus kvr plus lambda 1 into first derivative n minus 1th derivative of e plus lambda 2 n minus 2 derivative of e plus it continues lambda n minus 1 first derivative of e plus x n d dot. This becomes equation number 4. Okay guys, now let us continue this. We know that w tilde is given by the discrepancy between ideal weight vector and the estimated weight vector. Okay, so again I go back. Okay, w tilde, which is nothing but the weight vector error, is given by the difference between ideal weight vector and the estimated weight vector. Therefore, we can write x n dot is equal to w tilde transpose phi plus kv into r plus lambda 1 first derivative n minus 1th derivative of error plus lambda 2 n minus 2 derivative of error, and it continues plus lambda n minus 1 first derivative of error plus x n d dot. Okay. So, this equation can also be written in this way, that is x n d dot minus x n dot equal to nth derivative of error, which is equal to minus w tilde transpose phi minus kv into r minus lambda 1 n minus 1th derivative of e minus lambda 2 n minus 2 derivative of e minus lambda, it continues minus lambda n minus 1 first derivative of error e. So, this be equation number 5. Now, by differentiating equation 2 yields r dot equal to nth derivative of e plus lambda 1 n minus 1th derivative of error e plus lambda 2 n minus 2 the derivative of tracking error e, and it continues plus lambda n minus 1 first derivative of tracking error. So, this be equation number 6. Okay. Now, let us substitute nth derivative of the tracking error from the above equation number 6 into equation number 5. That yields r dot minus lambda 1 multiplied by the n minus 1th derivative of e minus lambda n minus 1 first derivative of e, which is equal to minus w tilde transpose phi minus kv into r minus lambda 1 into first derivative of n minus 1th derivative of e minus lambda 2 n minus 2 derivative of error e minus, it continues minus lambda n minus 1 first derivative of e, or we can precisely say r dot equal to minus kv into r minus w tilde transpose phi, that is equation number 7, because this and this will get cancelled. Okay. So, r dot equal to minus kvr minus w tilde transpose phi is equation number 7. Now, consider a Lyapunov function candidate that is given by say V equal to half R square plus half W tilde transpose gamma inverse W tilde. Say this be equation 8. So, here we know that gamma is a positive definite matrix. Okay. So, now let us continue this. Let us differentiate equation 8, that is the Lyapunov function candidate is derivated in order to give V dot equal to R dot plus W tilde transpose gamma inverse W tilde dot, that is being equation 9. Now, substitute R dot from equation 7 into equation 9, into the equation 9 we get V dot equal to R into what is R dot from equation 7, it is minus KVR minus W tilde transpose phi, that is, but the second term W tilde transpose gamma inverse W tilde dot, that is equation number 10 now. Okay. Since W is a constant, W tilde dot becomes minus W hat dot. Okay. Now, V dot becomes minus KV into R square minus W tilde transpose phi R minus W tilde transpose gamma inverse W hat dot. Thus, V dot can be further written as minus KV R square minus W tilde transpose taken out phi R plus gamma inverse W hat dot, that is equation 11. Now, we can have the second term of equation 11 being equated to 0. This equation equated to 0, we have phi R plus gamma inverse W hat dot equal to 0, which implies W hat dot being minus gamma multiplied by phi into R. This is the update law that we have seen in the initial stage of this lecture. Okay, that is equation number 12. This is the update law. So, now using this update law, which is given by equation 12, equation 11 becomes, by substituting this back, we have V dot equal to minus KV into R square, that is equation number 13. Okay. So, we can talk about this stability further in such a way that since V greater than 0 and V dot less than equal to 0, it proves stability of the system in the sense of Lyapunov. So, that R and W tilde are bounded. Thus, the verification of the theorem. Okay, this is the proof of the theorem. Now, let us see furthermore, integral 0 to infinity minus V dot dt is less than infinity, and V double dot is equal to, from V dot, V double dot is equal to minus 2 times R KV into R dot, and all the signals on the right hand side of equation 7 verify the boundedness of R dot as well as V double dot. Therefore, V dot is uniformly continuous. Thus, we can say V dot is uniformly continuous. Okay. So, according to Barbellet's theorem, V dot tends to infinity as V dot tends to 0 as t tends to infinity. That is according to Barbellet's lemma, you can say. Since V dot equal to minus kV r square in our case, V dot will be 0 only when r is 0. Okay. So, this is the situation. Thus, we can say that r converges to 0 with factor time. Since equation 2 represents a stable dynamics, the output tracks precisely the output tracking error E of t also vanishes with time t. Okay. As we know that it is r is the filtered error of the tracking error, we can say that r converges to 0 as time tends to infinity. Equation 2 represents stable dynamics as well. So, the output tracking error E also tends to 0 when time tends to infinity. Now, let us consider the last portion of this topic, which is nothing but inclusion, that means epsilon which is not equal to 0, that means the RBFN approximation error not equal to 0. When this is the case, now what will happen? Let us now assume a non-zero. So, assume a non-zero RBFN approximation error epsilon, which is bounded by a small number which is positive number epsilon n. Therefore, we can say that original function f of x is given by f of x equal to w transpose phi of x plus epsilon, where epsilon is bounded by strictly bounded by epsilon n, which is bounded by the boundary or the positive number epsilon n. Okay. So, with this modification, the time derivative of the Lyapunov function candidate V dot becomes r into minus kvr minus w tilde transpose phi minus epsilon minus w tilde transpose gamma inverse w hat dot, which is say equation number 14. Okay. So, now considering the same update law. So, considering the same update law, that is w hat dot equal to minus gamma phi into r, we get V dot equal to minus kV r square minus epsilon into r. Now, V dot can be further expressed as V dot less than equal to minus kV r square plus norm of epsilon r, or V dot is less than equal to minus kV r square plus epsilon n norm of r, because we have epsilon bounded by epsilon n. Okay. So, this is equal to minus r norm into kV norm of r minus epsilon n. Okay. So, this is the case here. Now, if your kV into norm of R minus epsilon n is negative, the above expression will be negative as well, will be negative. So, in other words, I can say kV into norm of R minus epsilon n greater than 0 or norm R greater than epsilon n by kV. Okay. So, this implies that V dot is negative definite as long as R norm greater than epsilon n by kV. Okay. So, that is the case which we can say that R is inside a ball of radius which is given by epsilon n by kV. Thus, by choosing kV to be larger, R can be made smaller, facilitating the tracking task. With this, I come to the conclusion that in this class we have seen feedback linearization and then RBFN based feedback linearization with f of x unknown, but g of x known with RBFN approximation error equal to 0 and not equal to 0. Thus, I can say that I am going to conclude now this lecture in such a way that we have seen the introduction to feedback linearization control algorithm, and then we have moved to neural network based feedback linearization, where the neural network considered is a simple one hidden layer based RBFN, where we are approximating the unknown function f of x by the output response of the neural network, with the consideration of two cases. One is with the RBFN approximation error being 0 and the another case with the error being non-zero. Thank you so much for your time.